Howdy, and welcome to Mean 315, lecture number 15. Let me just go through some announcements here real quickly with you. So, of course, homework number 6 is due on Tuesday, October 15th, and remember that it's due at 3 o'clock at 321 Mechanical Engineering Office Building, or the MIA building. And it's due, of course, to this room because, as you probably already know, or hopefully you should know, that lecture number 15, the lecture that would have taken place during class on October 15th, has been canceled, and we're disseminating the information through our video means that we're doing here. So homework number 6 is due by 3 p.m. at 321 Mechanical Engineering Office Building. It's my office. There's a wire basket outside my office, so please be sure to just put your homework in one of the 3 bins there, and the grader will collect it at 3 o'clock. The second announcement is that homework number 7 is assigned and available on e-learning, and homework number 7 will be due next Tuesday, October 22nd, and of course that'll be due in class. We will of course be having class next week. Project update number 2 is due on Thursday, October 17th, and be sure to look at the lecture notes from lecture number 13 if you're looking for some guidance on what that project update should entail. And also be sure to read the project information that's on the e-learning discussion board if you're looking for guidance on the project. And of course, if you feel lost or that you don't have enough guidance on doing the project, then just send me an email and I'll be happy to either discuss things through email with you or meet with your group if you'd like to meet as a team. The fourth announcement is that the participation assessment on Thursday, October 17th, the next time that we're getting together for lecture, is graded. Remember that that participation assessment is going to cover material from lecture number 14 and this lecture, lecture number 15. And that participation assessment is graded, which means that in order to receive credit for participating, you need to answer the questions correctly, not just respond with some answer. So be sure to review the lecture notes from lecture number 14 and this lecture, lecture number 15, in order to be successful on that participation assessment. Okay, so just to pick up where we left off last week, you remember that we've spent quite a bit of time talking about steady state systems, and last week we spent most of our time talking about what we call work devices. And in the case of a work device, of course, that necessarily means that the work does not equal 0. The whole purpose or the function of that steady state device that we're modeling is in fact to produce work. So work should not equal 0 when we're analyzing work devices. And examples of work devices are turbines, compressors, and pumps. And of course, we also spent quite a bit of time last week talking about an efficiency characteristic that we can define for these work devices, where the efficiency characteristic that we use for a turbine is what we call eta ST, where S stands for isentropic and T stands for turbine. And of course, eta stands for efficiency. So eta ST is the isentropic efficiency for a turbine. And likewise, we have an efficiency calculation for compressors, the isentropic efficiency for a compressor, and we can use that same definition that we use for a compressor to define the isentropic efficiency for a pump, eta SP. This week, we're going to talk about the other type of steady state systems that we frequently analyze, and those are the devices that are not designed to transfer work. In other words, they're designed for some other function than just to transfer work energy. And so I collectively call these non-work devices. And naturally, in the case of non-work devices, most of the time the work transfer is going to equal 0. So the typical non-work devices, and what we're going to spend this week talking about, include devices such as nozzles and diffusers, throttles, mixing chambers, pipe flow or duct flow, or heaters. And I combine all these together because the analysis of these 3 are all very much the same. And then finally, heat exchangers. So we're going to go through and discuss each of these different devices. And what you'll find is that once you know what each of them does, what their purpose is, then actually doing the thermodynamic analysis of them is pretty straightforward. There aren't any, there really aren't any conceptual difficulties with analyzing any of these devices. It's really just a matter of knowing what they are and what their function is. Now, the one item that I did want to point out is that in the case of a nozzle, and in fact in the case of a diffuser, nozzles and diffusers, even though they're non-work devices, they manipulate mechanical energy. So what does that mean? Well, as we're going to talk in just a minute, nozzles are designed to use the pressure of a substance to increase its kinetic energy, or its velocity, the velocity of the flow. So a nozzle is designed to increase velocity of a flow. So you're going from one type of mechanical energy, that's pressure energy, and going to a different type of mechanical energy, that's kinetic energy or velocity. So because we're doing that in the case of a nozzle, we can correspondingly define an isentropic efficiency. We can model the nozzle as being adiabatic. In other words, you don't have to have heat transfer in order to do that mechanical energy change from pressure to kinetic energy. And so we can treat the nozzle as being adiabatic and model that conversion as isentropic or no entropy generation, in which case we can define an isentropic efficiency of a nozzle. And so we'll do that in just a moment. Now, a diffuser also is just the opposite of a nozzle. So a nozzle takes mechanical energy and converts it into kinetic energy of the flow. A diffuser takes kinetic energy of the flow and converts it into mechanical energy. Now, interestingly, we don't often define an isentropic efficiency for diffusers, and I can't honestly say that I necessarily know why, but at the same time, I can't say that I've ever had a need or have had a specific a specific need to have that isentropic efficiency of a diffuser, because usually when we apply a diffuser in an application, we're looking to simply get some additional pressure rise by making use of kinetic energy. And so actually looking at different designs of diffusers to do that is not really a very common activity that's done. And so maybe that's why an isentropic efficiency for a diffuser doesn't exist. But I don't know precisely, so take that for what it's worth. So we're going to go through each of these different devices, and we're going to describe what they are, what their purpose is, and how we thermodynamically analyze them. So when we do that analysis, we're going to, of course, rely on the general steady state non-work, the general steady state first law equation. And of course, because we're doing this for a non-work device, in almost all cases, the W dot term in our first law equation will go to 0, okay? Now you'll notice in parentheses that I put usually here. So what that means is that, of course, you always want to pay attention if there's work transfer. And the one way that you always know if you have work transfer or not is if you're able to move something with that process or that system. So if you take, for example, a motor that has a spinning shaft, well, that spinning shaft can move things. I mean, it itself is moving because it's spinning, but you can move something else with it. You can attach that spinning shaft to a belt and have that belt drive a drill bit, for example. So that's an example of work transfer. Or the motion of a piston in a piston cylinder arrangement is work transfer because that piston can move other things. Or the lighting of your computer screen with electricity. Again, you're using electricity and you're exciting, photons and so on and so forth, but you're still moving things. And so in your transferring useful work, you can get useful work out of that. So don't let that make you feel nervous that this says usually here. I don't put that in there to try and trick you or create a stumbling block on an exam. I put this in here so that if when you're working as an engineer someday, that you don't just blindly cancel this work transfer term if you happen to be studying a steady state device that in fact does have work transfer with it. It's almost always obvious when you have a work transfer associated with your process. But I just put that in there for completeness of discussion. Okay, so what I've done below here is I've provided a little summary of what would happen to each of these terms in the first law equation. So for the first term, we have the Q dot, which of course is our heat transfer term. And when we're talking about non-work devices, this Q dot may or may not be equal to 0. It depends on what assumptions you can make, and it depends on what kind of device you're analyzing. So the one rule of thumb that you can safely rely on most of the time, there's just one exception. I don't mean to create all these rules and exceptions to the rules for you, but for any device that is designed to transfer thermal energy, such as heaters or chillers or condensers, Q dot, of course, is not equal to 0. Okay, if it's a heater, you're transferring thermal energy from the surroundings to the system, so necessarily your Q dot term would be non-zero. Now, the one exception to this that we're going to spend some time talking about today is a heat exchanger. And actually, the one exception with a heat exchanger is only when you draw your control system around the entire heat exchanger. And we'll get to that later on. I don't want to dive into the details right now, but just know that heat exchangers can sometimes be an exception where, of course, a heat exchanger is purposefully designed to transfer thermal energy, but there may be an instance, depending on how you draw your control system, where in fact there's no heat transfer between the heat exchanger system and its surroundings. We'll talk more about that later on. So the summation sign, right? So we've got Q dot plus the sum of m dot I times EI equals the sum of m dot E times EE. So when we do work devices, we very often canceled that summation if we had single flow in, single flow out conditions. So the same is also true in terms of dropping that sigma sign if we have single flow devices that are non-work devices. But one exception that will almost always be the case is if we're studying a mixing chamber. Mixing chambers always have multiple flows, right? You have to have more than one flow coming in order for it to be a mixing chamber. You're mixing two different things, so there has to be multiple flows at least coming in. And you may have multiple flows going out, but for sure you should have multiple flows coming in. So do be careful about just blindly dropping the summation sign when writing your first law equation for non-work devices, especially mixing chambers. And then, of course, the last term that's in our first law equation that we can make some general statements about is the energy of the fluid. So that's our E term. And remember that the energy of the fluid is the summation of its enthalpy. And remember that whenever we have flow, we have to use the enthalpy property, not just internal energy. This enthalpy, of course, includes the internal energy plus the flow work. So we have the substance's energy given by enthalpy, plus its kinetic energy, 1/2 v squared, plus its potential energy, g times z. Now, enthalpy, kinetic energy, and potential energy may or may not cancel. So again, when we did work device analysis, we were always able to cancel potential and kinetic energy. But in the case of non-work devices, these terms are not as commonly canceled. And so we have to really pay close attention to the situation that we're analyzing before we just cancel a kinetic energy or a potential energy term. Okay, so before we get too far into the details about non-work devices, let me just provide a summary of the work devices for you that we talked about last week. So of course we have turbines, and we can make our general statement that there's some flow in and some flow out. And for this particular situation, we're saying that there's a single flow in and a single flow out, and that it's transferring some work. And we're treating it as being adiabatic. I don't have a heat transfer term drawn between the system and the surroundings. And we know that the purpose of a turbine is to convert inlet energy, that is the enthalpy of the inlet flow, to work, right? So the purpose of a turbine is to create, or is to transfer work energy. And as we talked about last week, the typical assumptions that we make for a turbine are that it's adiabatic, in other words, the heat transfer is equal to 0, and we have negligible changes in kinetic and potential energy. So these are typical assumptions, not always, but that's typically how we do our analysis for a turbine. And so the first law typically becomes this form here, where it's just the difference between the inlet enthalpy and the exit enthalpy. We also talked about compressors and pumps, and of course a compressor / pump have the purpose of converting work energy into exit energy. In other words, we put work energy into the system so that we can get a higher exit enthalpy than the inlet enthalpy. And we talked about the difference between a compressor and a pump. A compressor is designed to increase the exit energy of a gas, whereas a pump is designed to increase the exit energy of a liquid. And we can make our typical assumptions for compressor or pump analysis. And the first typical assumption is that we treat it as adiabatic, so heat transfer is equal to 0. And we typically can neglect our kinetic energy and potential energy. And so we get our first law equation is the difference between the inlet enthalpy and the exit enthalpy. Same equation as the first law for a turbine equation. But the one item to note is that the compressor work or the pump work is going to be negative because the work is going into the control system. And so by virtue of this on the left-hand side being negative, the right-hand side will be negative, which means that the exit enthalpy is greater than the inlet enthalpy. Okay, so that's what we talked about last week, and we defined turbine isentropic efficiency and compressor isentropic efficiency. But now let's start to shift our attention to some of the non-work devices. So the first non-work device that we're going to spend some time talking about is what we call a nozzle. And a nozzle, we've all had experiences with a nozzle before. If you've ever played with your garden hose, for example, and you had a nozzle on the end of it that would allow you to, squirt water at your mom or dad or at the neighbor's dog or whatever the case may be. That was, of course, in fact, a nozzle. So the purpose of a nozzle, in the way that a garden hose nozzle works, for example, is that it converts pressure into kinetic energy. So when you put a nozzle on the end of a garden hose, you now have water pressure that's basically contained, if you will, behind that nozzle. And the nozzle, of course, has a change in area. And by virtue of that change in area, that pressure that's provided by the water supply system gets converted into kinetic energy. So you have relatively slow velocity but high pressure coming into the nozzle, and relatively high velocity but low exit pressure leaving the nozzle. Okay, so in the case of a nozzle, the work transfer is equal to 0. Okay, since of course you're not actually transferring any work in here, but you are converting one type of mechanical energy, that is the pressure energy, into a different type of mechanical energy, that is the kinetic energy leaving the nozzle. Now, before I dig into the assumptions in the first law equation, there's one thing that I want to bring to your attention about a nozzle, and that is the change in area for a nozzle. So the way that I have this drawn is probably the way that you would conceptualize a nozzle, in that the inlet area is greater than the exit area. And in your mind, that probably makes a lot of sense because, you've got slow velocity coming in, and then you neck that area down to a small exit area, and thereby, use that pressure energy to increase the kinetic energy of that exit flow. But what's probably not going to feel very intuitive to you is when I tell you that this design for a nozzle is only true if your flow is subsonic. In other words, less than the speed of sound. If your flow were faster than the speed of sound, or what we call supersonic, the nozzle would in fact have just the opposite area relationships. In other words, your inlet area would be smaller than your exit area. You'd have what is called a diverging design for a supersonic nozzle. So if you just ignore this E and this I here, this in fact would be your inlet side, and this would be your exit side if the flow were supersonic. The key thing though is that the function is still the same. So in other words, if I call it a nozzle, what that means is that my exit velocity is faster than my inlet velocity. So for supersonic cases, even though my inlet area is smaller than my exit area, my exit kinetic energy is still higher than my inlet kinetic energy for supersonic flow. The definition of the nozzle is a device that converts pressure energy into kinetic energy. And if you're wondering of a practical application or where you may actually see a supersonic nozzle, just look at the, they're called the exit nozzles on the space shuttle. So if you look on YouTube and you find in fact I can go ahead and do this right now for you, where we can find a nice picture here. Let's see if I can do this. So that wasn't very good. Yes, I do use Wikipedia. It's, I think, okay. Just pay attention to what you're reading. Okay, there we go. So this here is a picture of a, basically the exit of a shuttle engine. And you'll notice that this, in fact, is called the exit nozzle for the space shuttle. So, if you've ever seen a picture of the space shuttle, you know that there's three of these nozzles that are on the bottom of what had been the space shuttle. And so you'll notice that the inlet area is smaller than the exit area. And that's because the combustion gases, when they enter into this throat area here, they are in fact approaching the speed of sound. And so this nozzle is designed, in fact, to accelerate the flow of a supersonic flow, accelerate the velocity of a supersonic flow. And so the way this is drawn here is for a subsonic flow. Okay, so let's just make sure that we pay attention to that as you continue to design and use nozzles in your career. Okay, so what are the typical assumptions of a nozzle? Well, first of all, we can always pretty much assume that a nozzle is adiabatic, unless you're told otherwise, or you're dealing with some really high temperature gases or something that would not make it adiabatic, in which case your heat transfer term, of course, is equal to 0. Now, you're dealing with kinetic energy, so you cannot neglect kinetic energy. But you very rarely have any changes in elevation or significant changes in elevation, so you can neglect potential energy. So your first law basically becomes the following, where you have single flow in, single flow out. So you have your inlet enthalpy plus your inlet kinetic energy, 1/2 VI squared, equal to your exit enthalpy plus your exit kinetic energy. Now this is cut off down here, okay, but what this says is that this VI squared term is often negligible. Okay, so in other words, because you're accelerating your flow through the nozzle device, your exit velocity is usually several times larger than your inlet velocity, sometimes an order of magnitude larger than your inlet velocity. So you can very commonly neglect this inlet kinetic energy or this inlet velocity. In other words, assume that VI is equal to 0. Now, the other item that we talked about above is the fact that because we are converting from one type of mechanical energy into another type of mechanical energy, we can define an isentropic efficiency. So the isentropic efficiency for a nozzle is the actual exit kinetic energy divided by the isentropic exit kinetic energy. So of course, kinetic energy is 1/2 m dot v squared, and you have the same in both the numerator and the denominator, so your 1/2 m dots cancel, and so you're left with then the square of the actual exit velocity divided by the square of the isentropic exit velocity. And in order to do that isentropic analysis, you would essentially treat this nozzle as being reversible, no entropy generation, and adiabatic, Q is equal to 0, and then look at how your exit enthalpy changes compared to your, how the exit enthalpy for the isentropic nozzle compares to the exit enthalpy for the actual nozzle. And then use your first law equation to come up with an actual exit velocity or an isentropic exit velocity, depending on what information you have available to you and what you have to solve for. Okay, so that's a nozzle, and so the next device that we'll study is what we call a diffuser. And as I mentioned, a diffuser is basically exactly the opposite of a nozzle. So a nozzle is designed to convert pressure into kinetic energy. A diffuser is just the opposite, where it converts kinetic energy into pressure. Now the way that a diffuser works is you have this inlet area, and again, this is drawn for subsonic flow. That's very important to note that this is drawn for subsonic flow. If it were supersonic flow, it would be the same issue or the same idea that we had with the nozzle, where this in fact would be the inlet side and this would be the exit side if this were supersonic flow. So in the case of a diffuser, the flow comes into a small, the subsonic flow comes into an area, an inlet area that's smaller relative to the exit area. And this, in the way to think about this is the following. You have this increasing area when you have subsonic flow, and that kinetic energy continues to pack in more and more molecules into this expanding area. And so the diffuser, by virtue of this expanding area, is able to take that kinetic energy as it decelerates that energy filling up this larger and larger area. It's able to convert it into mechanical pressure or a higher pressure. So the purpose of a diffuser, as I mentioned, is to convert kinetic energy into pressure energy. Now you probably, there's diffusers are sometimes hard to imagine or hard to see, but there's actually two very good examples of diffusers. And so again, since I can just do this real easily, the one example that's always kind of fun to think about is the inlet diffuser of a jet engine. Let's see what this can show us, if we can get a good picture of this. So let's see here. No, that's the exit, so that's not a good picture. I don't see any good pictures here. It would be good if I could get the front side of that turbine fan there. Oh, here we go. I think that might be a good picture. Plus, it's kind of cool. I don't know what's going on in the back there. Okay, it's a little bit hard to see because it's so dark, but I guess you can see it a little bit here. So do you see, if you see my mouse, you see how there's that curvature in the jet engine where you have this, basically the cross-sectional area of this jet engine increases as it gets into the midsection of the engine. So this opening area is smaller than this midsection area. You see that? See how that curves down and makes this opening area have a smaller area than the midsection area? Well, this section in here is a diffuser. You have a smaller inlet area. Jet engines or jet airplanes, typically, not all of them, there are some exceptions, fly less than the speed of sound. And so you have subsonic flow conditions. So but you also have a high amount of velocity, right? This jet engine is going to be flowing through the sky at say 500 miles an hour, for example. So there's a tremendous amount of kinetic energy that if you use a diffuser, you can convert that kinetic energy into a substantial pressure rise through the midsection of the jet engine before it enters the compressor stage. And so this inlet area here is purposefully designed smaller to make this opening entrance actually a diffuser, to make this, in fact, a diffuser. And so just to kind of give you the different parts of the jet engine, because jet engines are kind of cool, you have this opening area here, which is the diffuser. So your diffuser stage goes until about right here, and then that starts your compressor stage. So your compressor stage is basically where you have compressor blades that further increase the pressure of the air that's being inducted into the jet engine. You then, at about right here, have what is called the combustor stage. So this is where you have fuel jet nozzles that squirt jet fuel into the now compressed air, and that jet fuel, of course, is mixed with the air, it's ignited, and then you have combustion that takes place in here. So then you have really high temperatures, really high gas pressures, and those gas pressures then partially expand. They don't completely expand. They partially expand through a turbine stage, which is about right here. And the sole purpose of that turbine is to provide the mechanical work to spin your compressor blades that are at the front of the engine. So you have a turbine stage back here that's driven by your combustion gases and mechanically connected with a shaft that runs the length of the engine to your compressor blades that pressurize that air that's later used for combustion. But then where all the neat stuff happens is on the tail end here. So this last part of the jet engine after the turbine stage is where the nozzle is. Okay, so your jet engine actually has a diffuser and a nozzle in it, and I can show you some of these different. That's a supersonic design. That's why it's designed a little bit differently. So here we go. So this backside here, this doesn't have a diffuser designed into it. So you have your compressor blades. They sometimes call that the fan. You then have, this is your mechanical shaft. You have your combustion. This is where your combustion takes place. And then you have your turbine stage, which serves the sole purpose of just driving this compressor stage on the front end. And then those gases that leave the turbine side are then expanded through a nozzle where you then take that very high pressure gases that are in this region and you accelerate them through this nozzle, which then of course gives you the high exit velocity and gives you your thrust of your jet engine. Okay, anyway, that's one area that you would see a diffuser. But then the other area is, let's see if we can pull up another example of, no good. Not getting the images that I want here. Let's see, I don't know why I'm getting, oh, here we go, but that's not Texas A&M, that's some goofy school up in Arkansas. Yeah, okay, well, I won't be able to find one that has Texas A&M on it. That's too bad. Okay, I guess our yell leaders don't need megaphones. I know that's what you're thinking, and I should know this, but I'll just do a general search for a megaphone then. So let's see what we get here, and we'll find here. This is a good neutral, good neutral megaphone, right? So of course you know how this works, right? You've got some person that already has a big mouth that's standing on this side, and they're shouting into this small end. And this megaphone is designed to basically amplify their voice so that the exit is much louder and can reach into the far reaches of a large stadium or a large group of people. So this is in fact a diffuser, right? When you shout into this small end, what your voice is doing is it's projecting with a velocity the sound, okay? But in order for that sound to be loud enough, that's actually a pressure phenomenon. So if you remember studying sound at all in Physics 218, for example, then you know that the decibel scale is in fact a variation of pressure amplitude. And so what you really need to do is you need to increase the pressure of that sound if you want it to be amplified to go longer distances or to be heard louder by a group of people. And so a diffuser or a megaphone is a diffuser that amplifies a person's voice by taking the kinetic energy that our lungs supply and converting that into a pressure rise through this larger exit opening. Okay? All right, so even though they look kind of strange, you actually have a lot more experience with diffusers than maybe you knew before. So what are the typical assumptions? Well, diffuser analysis is very similar to nozzle analysis. They are, after all, just the opposite. So a typical assumption of a diffuser is that, first of all, it's typically assumed to be adiabatic, so the heat transfer is equal to 0. And when we apply the assumptions of it being adiabatic and negligible potential energy, then of course our first law equation looks exactly the same as the nozzle first law equation. And the one difference between the nozzle and the diffuser is that, whereas in the case of the nozzle, we could typically assume the inlet velocity to be negligible, it's the exit velocity that is negligible in the case of a diffuser. Okay, so those are nozzles and diffusers. Now, the next thermodynamic device is, in fact, what we would call a throttle. And, again, this is kind of fun. I can pull up all kinds of crazy images about these things and show them to you. So I'll bring up an image of a throttle, but of course, you probably already know or suspect that a very common application for a throttle is... Anyway, so this is a little bit hard to see here because it's kind of dark, but what you see here, well, first of all, you see these two openings, right? So those are basically the inlets to the engine, how the engine breathes air, okay? And then, now if you look real closely, you see how there's a circular plate here, okay? And it's on its side, and it's connected, and there's two of them. Here's a second metal plate. And there's a shaft that runs between them that these metal plates are basically screwed to that shaft, okay? So that when the shaft moves, the plates will open and close in what is called a butterfly fashion. So we would call this a butterfly valve, okay? And so when you step on the accelerator, so this, it's hard to tell for sure, but this looks like this might be the cable that connects to the accelerator pedal. When you push on your accelerator pedal, ordinarily, these plates are actually in the down position, so they're folded or they're turned down so that they're closing these inlet passages, okay, and not allowing any flow of air to enter into these inlet passages. But when you step on the accelerator, you actually start to pull these, you pull this cable, and oops, sorry. Let me go back here. Okay, there we go. So this cable gets engaged when you push on the accelerator pedal. That turns this shaft that runs the length here, and then that causes these blades, these butterfly valves, to in fact open and thereby allow the engine to breathe more air. But what you can already tell is that the way that a throttle works is by restricting airflow, right? Its function is to restrict flow. So if we now go back to the lecture notes, what we see is that what a throttle's purpose is really just to decrease the pressure of the flow. We said when we were looking at the images that it's designed to restrict the flow, but it restricts the flow by decreasing the pressure of the flow. Okay, in other words, if you just imagine you have this this plate that's blocking the flow, and the engine is the reciprocating pistons in the engine are trying to induct air into the cylinders, so they're actually putting a vacuum on those throttle plates. But because the throttle plates are closed, restricting that airflow, it creates a vacuum or a pressure decrease across that flow path. So the purpose of a throttle is in fact to decrease the pressure of flow. So we typically draw a throttle as follows, right? So we have this pipe or this passage, and there's a restriction in it. Okay, so these two little bars that you see here, these two little lines, represent a restriction or a momentary area reduction. So you have your inlet flow that's coming in and your exit flow. And of course, the inlet pressure is greater than the exit pressure. Okay. And the typical assumptions that we make are, first of all, that it's adiabatic. So we say that our heat transfer is equal to 0. And we also say that we have negligible kinetic and potential energy. So when we look at our first law equation, what that means is that a throttle is typically isenthalpic, or constant enthalpy. In other words, the inlet enthalpy is equal to the exit enthalpy. And what's kind of interesting is that if you have an ideal gas, you know that the change in enthalpy is equal to Cp delta T. So in this case, the change in enthalpy is equal to 0, right? The inlet enthalpy is equal to the exit enthalpy. So that means that the change in temperature of an ideal gas being throttled is equal to 0, okay? So that's kind of just an interesting point that is good to keep in mind for future information. So the next device then that we'll talk about are what we call mixing chambers. So as you might suspect, the idea or the purpose of a mixing chamber is to mix two or more streams into one or more stream. Now typically it's two streams that are being merged into a single stream, but there's no reason why you might not have n number of inlet streams and n-1 number of exit streams. Or you could have more than one, you could have more exit streams than your inlet streams. That just means that you're supplying more than just the number of inlet streams that you had coming in with the mixed item, or the mixture basically. So our typical assumptions with a mixing chamber are that it's adiabatic, so the heat transfer is equal to 0, and we have negligible kinetic and potential energy usually. And so then our first law equation typically becomes now the sum of the mass flow rate of the individual inlet streams times their respective enthalpies, and that is equal to the sum of the exit mass flow rates times the enthalpy of the exit flows. Okay, so the sum of m dot I hi is equal to the sum of m dot E he. So in the case of the simple example that I have drawn here, where there's two inlet flows and one exit flow, the first law equation would be m dot 1 times h1 plus m dot 2 times h2 is equal to m dot 3 times h3. That would be our first law analysis for this mixing chamber. Okay, so all of the devices that we've talked about so far are basically devices that can typically be modeled as adiabatic or heat transfer equal to 0. Okay, so let's now start to shift our attention to those steady state devices that are specifically designed to transfer thermal energy. Okay, so the first category of devices that we study are what we call pipe flow or duct flow, or this is also the category that we can put heaters and chillers and condensers, because the analysis is basically the same, even though of course a length of pipe is not the same as a heater, but it's all very similar conceptually in terms of how we would analyze them thermodynamically. So let's suppose that we had a piece of pipe, or we can call this a heater, if you will. And of course, the function of a heater is to add thermal energy from the surroundings into the system. So we have Q dot that's drawn from the surroundings into the system, and we have an inlet state and an exit state, where of course the exit state is going to have a higher amount of thermal energy than the inlet state by virtue of adding that thermal energy from the surroundings. So the purpose of pipe flow or duct flow or heaters or chillers or condensers is to add or remove thermal energy from the system, or in this case what we would specifically call the flow. So our typical assumptions, again, are listed here, where we have usually negligible kinetic and potential energy. And so our first law equation, the typical first law equation, looks as follows, and I realize that you can't see that. So let me see here if there's a way that I can type this out for you. So if I click on this guy here, and let me bring this guy over, and if I start typing, will this work for me? Here we go. And so we will say that this is Q, see if it'll do this for me, dot okay, so that's supposed to be Q, not G. Is equal to M dot I. Now you know why I write this out ahead of time. That's M dot I. Okay, that's supposed to be M dot I, not boot. This is quickly becoming a failed experiment. So before I create any problems here, I'm going to just cross that out and abort here. Okay, so when we apply the assumptions that we have negligible kinetic and potential energy, our typical first law is as follows. We get that Q dot plus this is M dot I times HI is equal to M dot E times HE. Okay, so, and again, when you do the analysis, you'll have, you should be able to have information to find out M dot I. You'd use your property information to find HI and HE, and that would let you solve for Q dot. Or maybe you're given Q dot in your state information and you have to solve for M dot, whatever the case may be. But single equation, so you would only be able to have at most one unknown to use just the first law equation to analyze pipes, duct flows, or heaters. Okay, so the last device that we're going to talk about today is what we call heat exchangers. And so if you remember, when we started the lecture, we said that there's actually potentially a way an analysis of a heat exchanger where it would in fact be adiabatic, or Q is equal to 0. So I'm going to walk you through that, but before we do that, let me just specify or tell you that the purpose of a heat exchanger is, of course, to transfer thermal energy from one fluid to a different fluid. Okay, that's what's very important about the definition of a heat exchanger. A heat exchanger is not necessarily designed to transfer thermal energy from the system to the surroundings. Okay, so that would be the case of a heater or chiller or condenser, whatever the case may be. So most heat exchangers are what we would call two-fluid heat exchangers, where you have one fluid that comes in, and so we'll call this fluid A, and that fluid flows into the heat exchanger device and flows around and thermally communicates with a second fluid, which in this diagram we're calling fluid B. And so fluid A may, for example, come in at high temperature, and fluid B may come in at low temperature. And so fluid A transfers its thermal energy to fluid B, such that fluid A cools down and leaves at a lower temperature at state 2, and fluid B accepts that thermal energy, heats up, and leaves at a higher temperature at state 4. Okay, so let me again see if I can find some good images for you of heat exchangers. Okay, so this is probably, actually this, well, I can look at both of these. So a very common design of a heat exchanger is what is called the shell and tube heat exchanger, okay? And so in the case of a shell and tube heat exchanger, you have two fluids. So you have the green fluid, okay? And then you have the second fluid, which in this case is the blue fluid, okay? Now, the reason why this is called a shell and tube heat exchanger is because the whole unit, the whole heat exchanger, is made out of a piece of pipe, basically. And then what's inserted into this pipe are a series of tubes that are connected on both ends by what is called a tube sheet, okay? And the tube sheet is basically a plenum, or a manifold, if you will, that allows the one fluid to only flow through the tubes, okay? So this tube sheet basically blocks this fluid, this green fluid, from mixing in with the second fluid, which is what this diagram is calling the shell fluid, okay? And so your green fluid flows in, and it flows through these length of tubes here, right? You see these green lines that are running the length between the two tube sheets. So your green fluid flows in and flows through one of these several tubes that are in this shell and tube heat exchanger. And by flowing through those tubes, you then have your other fluid that flows in and basically flows around the outside of those tubes, okay? And so the two fluids don't ever mix with each other, but because of the fact that these tubes, for example, are made out of metal, they transfer thermal energy, so they don't physically mix, but they thermally communicate with each other. So the hot fluid can give up its thermal energy to the cold fluid. And so after that heat transfer takes place between the two fluids, the tube fluid flows out the one side and the shell fluid flows out the other side, okay? Now there's an additional level of detail that's in here, and that is that this particular shell and tube heat exchanger has what is called baffles built into it. And what these baffles do is they just help increase the mixing of the shell fluid with the tubes, because otherwise what would happen, these are usually very large volumes, and so what often can happen is you can have hot spots that form in different parts of the heat exchanger, hot spots and cold spots, so you get uneven heat transfer between the hot fluid and the cold fluid. So these baffles just basically make sure that the fluid on the shell side is flowing the whole diameter of the shell and avoiding the creation of any hot spots in one of your two fluids. Okay, so this is my replication of a heat exchanger, right? So fluid A may be the shell fluid, for example, and fluid B may be the tube fluid, for example. But the point is that the two are able to thermally communicate with each other and exchange thermal energy from the hot fluid to the cold fluid. Okay, now there's two ways to analyze a heat exchanger, and the two ways depend entirely on how we define the control system. If we define the control system as the entire heat exchanger, okay, so if I take my dashed line and I draw it around the entire heat exchanger, okay, well, that is the case where I can, in fact, consider the heat exchanger to be adiabatic. In other words, the thermal energy takes place inside the heat exchanger. It takes place between fluid A and fluid B inside the heat exchanger. So the heat exchanger isn't necessarily designed to transfer thermal energy from either fluid to the surroundings. And when you're drawing your control system around the entire heat exchanger, you're capturing that fact that this could in fact be an adiabatic control system. Okay, so if you say that the entire heat exchanger is your control system, then it becomes an adiabatic system, or it can be modeled as an adiabatic system. And as you might expect, we're able to neglect kinetic and potential energy. So our first law then becomes the following. our Q dot is gone because it's adiabatic. Our W dot is gone because it's a non-work device. And so the first law says that m dot I times HI plus m dot 3 times H3. So this is the inlet energy of fluid A, and this is the inlet energy of fluid B. And this is balanced by the energy that flows out. So m dot 2 H2 plus m dot 4 H4, where this m dot 2 H2 is the exit energy of fluid A, and m dot 4 H4 is the exit energy of fluid B. Now, when you draw your control system around the entire heat exchanger, this is actually not very helpful. What it means is that you have to know information about both of your flow rates, m dot of fluid A and m dot of fluid B, and you have to have your property information for 3 of your 4 states. And perhaps you use this equation to determine your 4th unknown state, for example. Or maybe you have all 4 states fixed and you have to determine your mass flow rate of fluid A or the ratio of flow rate A to flow rate B or something like that. That's really the only time that this first law equation drawn around the entire heat exchanger is ever really helpful. If you want to know details about this thermal energy exchange between the 2 fluids, then you can't draw your control system around the entire heat exchanger. Remember that the moment that you draw your control system, what you're basically saying is you don't really care about how the control system is changed. You don't care about those details inside the control system. That's why you've drawn your control system that way, is to capture or to not need to capture those details. So that then brings in the second way to analyze a heat exchanger, and that is to draw your control system around just one of the fluids. Okay, so that's the second analysis here. So now we're drawing our control system around one of the fluids, and just for convenience, I simply said that I'll draw my control system around fluid A. So fluid A, if I go back up to this picture here, enters at state 1 and exits at state 2. So we have fluid A entering at state 1 and exiting at state 2. And because fluid A inside the heat exchanger, but that's not my control system anymore, so I have to pay attention to now the energy exchanges between my system and my system is fluid A, and the surroundings to fluid A is fluid B. So fluid A is transferring thermal energy from its system, that is fluid A, into its surroundings, which is fluid B. So this Q dot here is the thermal energy transfer from fluid A to fluid B. Okay? So again, we can assume negligible kinetic and potential energies, but we can no longer assume adiabatic, right? Because it is in fact designed to transfer that thermal energy. So our first law equation then becomes the following. It looks just the same as the first law equation does for a heater, where we have the heat transfer rate, Q dot, plus the energy in rate, m dot 1 times H1, which is equal to m dot 2 times H2. So for fluid A, if you know the mass flow rate, m dot 1, which is of course the same as m dot 2, and you know your inlet and exit property information, H1 and H2, then you can calculate what the thermal energy transfer rate is between fluid A and fluid B. Now, once you know that Q dot, all of that thermal energy is transferring from the system, fluid A, into the surroundings, fluid B. So what that means is that if this Q dot, we'll call this Q dot A to B, that Q dot A to B is exactly the negative of the heat transfer that's being absorbed by fluid B from fluid A. In other words, Q dot A to B is equal to negative Q dot B to A. That is, the heat transfer from fluid A to fluid B is equal to the negative of the heat transfer from fluid B to fluid A. Okay, so that's basically a snapshot of our steady state devices, steady state non-work devices. And again, it seems like we've gone over a lot of details here, but really the only thing that you need to remember about steady state devices are what their purpose is, what their function is, and what are the standard assumptions that we make about these steady state devices. If you can get yourself that far, you'll be able to modify your first and second law equations. We didn't go over the second law equations here, largely because we would use the second law to either fix an exit state if we were doing isentropic analysis, or to help us calculate entropy generation if we wanted to determine if a process were reversible, irreversible, or possible, for example. Okay? But once you know what the purpose of the device is and what the standard assumptions are, then you can modify your first and second law equations for these various devices and proceed to do your analysis. In other words, there's no benefit or need to memorizing these specific equations for all of these devices. Okay, so once again, we managed to end a little bit early, but that's okay because we're in fact right on track. And so when we come back together on Thursday, on October 17th, we'll be able to continue our discussions about steady state non-work devices. If you have any questions, send me an email or post them to the discussion board. I'm always happy to address your questions in any venue that you feel comfortable with. Thanks very much for listening, and have a good day.